Yes, sir. On behalf of Mechanical Engineering Department, AD Patel Institute of Technology, a Constituent College of CVM University, I would like to welcome all the participants and our session guest, Dr. Anupam Dewan, sir. I would like to ask Dr. Mitesh Shah to introduce our expert today. Over to Mitesh Shah, sir.
Very good afternoon to all, and a very warm welcome to. It's my pleasure and privilege to introduce Professor Anupam Dewan, sir, in the Faculty Development Program sponsored by AICT AQIS scheme at ADIT, CVM University. Professor Anupam Dewan has more than 23 years post-PhD experience. He is a product of 4 reputed institutions. One is NIT Kurukshetra, where he obtained his bachelor degree in mechanical engineering in 1989. Then after, he went to IISc Bangalore, where he obtained his master's and PhD degree in 1991 and 1996, respectively. Both in mechanical engineering he did. Then after, he joined to IIT Guwahati, where he earlier worked as assistant professor, then after associate professor, and then professor in Department of Mechanical Engineering from 1997 to 2009. And then after he came to IIT Delhi, where he is R.C. Malhotra Chair Professor, Department of Applied Mechanics. Earlier he was chairperson in Department of Applied Mechanics Research Committee for 2 years, 2018 to 2020. He earlier had visiting professor position at University of Karlsruhe during 2000 to 2001 and University of Illingen, Nuremberg during 2004 to 2005, both among leading German technical universities. He was a recipient of the prestigious Alexander von Humboldt Fellowship, Germany in 2004 to 2005. He has authored the book Tackling Turbulent Flows in Engineering, published in 2011, which is referred the world over, and 5 chapters in international. Involved as a PI as well as co-PI with a sponsored projects of funding worth rupees 9.52 crores. 9 of his PhD and 36 of his MTech students have been already awarded degrees. He has taught 21 different courses to a wide range of students. His areas of interest include computational fluid dynamics and heat transfer, turbulence modeling, renewable energy, and climate modeling. Professor Anupam Dewan has extensively published research articles in these areas, which includes 8 review articles in leading international journals. He is a Vice President, National Society for FMFP for January 2019 and an Associate Editor for the Proceedings of IMechE Journal, one of the reputed journal, Part C, that is the Journal for Mechanical Engineering Society from May 2020. He was earlier an Associate Editor of the Journal Sadhana, Academic Proceedings in Engineering Science from 2013 to 2020. Professor Dewan is also associated with many professional societies, like he is a fellow of IE India, he is a member of International Association of Applied Mathematics and Mechanics, Germany. He is a member of Aeronautical Society of India. He is a life member of ISHMT, very popular society for heat and mass transfer related things. He has been invited for 28 expo. He is a regular reviewer for the many international journals, and most of these are leading journals with his very high impact factor. He has 73 articles in international journals, 6 articles in Indian journals, 48 proceedings of referred international conferences. So in total, he has published more than 143 publications in the various journals as well as conferences. It's really a matter of pleasure for all of us to have with you, sir, and we will be happy to listen. Thank you, sir. You can start your presentation.
Okay. Thanks very much. Thanks, Dr. Mitesh Shah, Dr. Mr. Bala Dutt. I think Dr. Mitesh Shah was a student in IIT Delhi, right?
Sir?
You were a student at IIT Delhi earlier?
Yeah. I was there in 2006 to 2009.
With Professor Talukdar.
So Talukdar and Subbarao, sir.
Okay. So I will now switch off my camera in case it is required. We will get back. So are you able to hear me? Am I audible?
Yes, sir.
Volume is all right?
Yes,
Yeah,
sir.
fine, sir. Fine.
Okay. So I thank the organizers for giving me the opportunity to give this lecture, and it's really a privilege for me to share with you the topic of turbulence and its modeling. So I think I can presentations, a window. Share. So can you see the presentation?
Yes, sir.
Okay. So turbulence modeling and overview of turbulence. So the title of my lecture as given in the pamphlet is Turbulence Modeling and Overview of Turbulence Models. The title is slightly different here, but nevertheless the contents are same. So can I ask one or two participants to tell me what do they know about turbulence? What is turbulence? So are the participants allowed to speak now?
Yes, sir. They are allowed to.
So I basically prefer to have a dialogue. It's basically I want to interact and then teach, or teach and interact, both ways. So can anyone tell me what do we know about turbulence? So any answer?
Irregular motion of the air.
Fine, but this is one very small right answer, but a very small component. Anything else? Okay, so I will start now, and first I think about 8 to 10 minutes I will talk about the physics of turbulence so that we can understand. And then once we know what is the physics of turbulence or how complex it is, that means if we appreciate that, then I will talk about how to tackle turbulence. So that was the title of my book, and currently I continue to work in this area. So definition of turbulence, I hope you can see the slide. Please tell me if you are not able to see. You can see the slide. So a fluid motion in which velocity, pressure and other flow quantities fluctuate in time and space. So it's not just the velocity, but all flow quantities fluctuate in time and space. So when we say that fluctuate in time and space, it will become amply clear. So for example, you see this figure, can you see the figure clearly?
Yes, sir. Yes,
Yeah.
sir.
So initially for once or twice I will ask, and then if everything is clear, or if something is not clear, please point it out to me quickly. So if you see here, what we see on the y-axis is u. So that means the velocity in the x direction. Suppose you are sitting in a room and you have a coordinate system, and at particular point, using the coordinate system at a fixed point in the room, you want to see how the u velocity varies with time. So what you will do is you will have an instrument and you will measure it, and then you will get a signal like what you see here. Okay, so it has a lot of fluctuations with time, and you see a horizontal line. This is like the time average velocity. Okay, time average velocity, that means you take over a period of you take the average over a period of time. So speed of a fluid at a point continuously undergoes changes in magnitude and direction. That means velocity is varying in direction, means it has all the three components and it has a lot of fluctuations. And in a turbulent flow, swirl and eddy motion are very common as the bulk of the fluid moves in a specific direction. Even if suppose you take a flow through a pipe, the flow through a pipe goes in one direction, but if it is a turbulent flow, then as the bulk flow moves in one direction, the turbulent flow will have all the three components of the velocity, and all these components will have a lot of fluctuations. That means the velocity will vary with time, and also there will be swirl and the eddy motion. And turbulent flows you find everywhere. You find in any fluid flow you find is actually a turbulent flow. Atmospheric and ocean currents, blood flow in arteries, oil transport in pipelines, lava flow, flow through pumps and turbines, flow in boats and wakes, around aircraft wingtips. This is actually just a very, very small list. Almost all flows that we encounter in practice or in our surroundings or our neighborhood are actually turbulent. So one of you said that yes, there is irregularity. Yeah, fine. So turbulent flows are irregular in nature. So if they are irregular in nature, then the deterministic approach to turbulence is impossible. Rather, one relies on statistical methods. That means some kind of average or some kind of average method. So now we have seen that there are fluctuations in a turbulent flow. Where do the fluctuations come from? So any turbulent flow you take, so will be in some system, and there will be some inherent disturbances in that system. For example, if you are doing experiments in a room, in a laboratory room, then there will be some vibrations in the building sometimes, or if there is a flow through pipe and there will be some roughness. So fluctuations inherently come from disturbances. And now if there are fluctuations, they may be either damped out. When they damp out, these fluctuations will not grow, their effect will disappear. So how do they damp out? Due to viscous effects. This is very important, that they damped out due to viscous effects, or may grow by drawing energy from the free stream. So if they grow, then they need some energy. So now the next point says that for low Reynolds number. So if you take low Reynolds number, if we take two flows, one with low Reynolds number and another with high Reynolds number, and we say that what is the relative significance of viscosity, we will see that in the flow with low Reynolds number, the viscous effects are more. So then if the viscous effects are more, the viscosity has a tendency to damp out the disturbances because of its inherent nature. So for low Reynolds number laminar flows, so low Reynolds number means high viscosity means laminar flows, the kinetic energy of the flow is not enough to sustain the random fluctuations against the viscous damping, because the viscous damping is large. However, for high Reynolds number turbulent flows, the kinetic of the main flow supports the growth of fluctuations. And we know that the turbulence occurs at high value of the Reynolds number. For example, for flow through a pipe, the flow is turbulent for Re greater than 4000 approximately, where Re is defined based on the average velocity and the diameter. So first key characteristics of turbulence is that it is highly irregular. Then the other property is diffusivity. What is diffusivity? Diffusivity is in some sense like the mixing of the flow property. For example, if you take and you put sugar into it, if you put sugar into it and there is no fluid motion, then will the entire cup of tea will become sweet because of the sugar? Yes, but it will take yes, it will become, but it will take infinitely long time, because mixing of the sugar will occur at the molecular level. Now, if you stir the fluid with a spoon with the tea cup, then the sugar will mix quickly because of the convection. But if you stir it rather more rapidly, then the sugar will mix quickly because of the turbulent motion. So initially, when there is no fluid motion, it's because of the molecular effects. When there is a fluid motion, but the laminar, it is due to convection. And then when it becomes turbulent, it mixes very rapidly. So one key characteristic of turbulent flow is that it causes rapid mixing and increased rate of momentum, heat and mass transfer. So therefore, if you have a practical situation, suppose you have a heat exchanger, many of us are mechanical engineers. If you have heat exchanger, then you would prefer to have a turbulent flow in a heat exchanger because it will mix rapidly. And turbulent mixing is much stronger than that of the laminar flow, and also because of the molecular action. So one key characteristic is irregularity, other is diffusivity. Turbulent characteristic is another one is that it is a large value of the governing parameter. So we are mechanical engineers, so most of us are familiar with the Reynolds number. Reynolds number is the ratio of the inertia forces to the viscous forces. But suppose it is some other flow. Suppose it is a buoyancy driven flow. For example, the smoke coming out of a chimney or flow from a incense stick, agarbatti smoke. Then in that case, the governing parameter is not the Reynolds number, but it is the Grashof number. So turbulent flow always occur at high values of governing parameter, RE in most cases, but not in all cases. And how does it happen? Parameter, turbulence originates as an instability of laminar flows if RE becomes too large or if the governing parameter becomes too large. And the instabilities are related to the very complex interaction of viscous terms and nonlinear terms in the momentum equation. Okay, so just one question before I go to the next point. Can someone tell me what is vorticity? What is vorticity? Vorticity. Hello?
Yes, sir.
What is vorticity? So if the participants are not speaking, so I can otherwise continue if
Yes, sir. It's basically spin and rotation and motion.
Yeah, so vorticity is actually the curl of the velocity vector, and since there are all the three components of the velocity present in a turbulent flow, the turbulent flow is highly a flow with high vorticity will be called a flow highly rotational. So turbulence is rotational and three-dimensional because turbulence has all the three components of the velocity present, and these components of the velocity actually fluctuate. So turbulence is rotational and three-dimensional, and since the flow has fluctuations, velocity field has fluctuations, therefore vorticity will also be fluctuating. So turbulence is characterized by high levels of fluctuating vorticity, which is composed of eddies interacting with each other. And in this case, when there is a high level of fluctuating vorticity, vortex stretching is one of the principal mechanisms by which the intensity of turbulence is increased. So at large Reynolds number, this is very important, cascade of energy. There exists a continuous transport of energy from the free stream to the large eddies, and from these large eddies to a series of increasingly smaller eddies. The smallest eddies dissipate energy and destroy themselves. So what we are seeing is that turbulence has fluctuating vorticity, and what we are seeing here is that a turbulent flow has a wide range of scales, wide range of eddies, from the largest to the smallest eddies, and the smallest eddies lose energy and then they destroy themselves. And the large eddy actually large eddies take energy from the mean flow. Turbulence flow has irregularities. Turbulent flow has diffusivity, large diffusivity, which is very relevant. It occurs at large values of the governing parameter, and turbulent flows have 3D vorticity fluctuations. Okay, So what is dissipation? Dissipation is actually loss of energy. So turbulent flows are always dissipative. That means they also lose energy. And if there is a loss of energy, then we need to compensate for this loss of energy. Otherwise, turbulent flows cannot be sustained. So turbulence needs a continuous supply of energy to make up for these viscous losses. And if no energy is supplied, turbulence decays rapidly. But we have seen that once a flow goes into turbulent state, it does not decay because it takes energy from the mean flow. So turbulence, another thing is it's a continuum phenomena. Though the smaller scales, we have seen that there are wide range of eddies, but the smallest eddies are still much larger than the molecular dimensions. And therefore, it's a continuum phenomena. Turbulence is a continuum phenomena and governed by the equations of fluid mechanics. As the smallest scales occurring in a turbulent flow are ordinarily far larger than any molecular length scale. The last point on this screen is very important. Flow phenomena. Turbulence is not a feature of fluids but of flows. For example, what it means is, suppose we take one particular fluid, air, but we take air in different situations. For example, air in wind turbine, air past aircraft wing, and aircraft in atmospheric boundary layers, or any other situation. So it is the same fluid, air. But if it is in different flow situations, then the characteristics of turbulent flows will be different, because turbulence is not a feature of fluid, of a particular fluid, but is of flows. And the three examples that I gave you for air, say in atmospheric boundary layer or aircraft wings or wind turbines, all the three geometries, in all the three geometries, the flow configuration is different. And therefore, the turbulence will be different. And it also happens that sometimes most of the dynamics of the turbulence is same in all fluids, whether gases or liquids. So why turbulence is a flow phenomena? Because its major characteristics are not controlled by molecular properties of the fluid in which the turbulence occurs, except close to a wall. So we also know that since turbulence is 3D and unsteady with very large fluctuations, therefore, and what is the governing equation for turbulent flow? Navier-Stokes equation. And we know that Navier-Stokes equation does not give a solution for such kind of problems, 3D unsteady problems. So since there is no general solution to the Navier-Stokes equation, and therefore there is no general solution to problems in to turbulent flows, and since every flow is different, you are sitting in a room, there is a flow, it's different. You are out in an air conditioning duct, the flow is different. Therefore, every turbulent flow is different, even though all turbulent flows may have common characteristics. So in this course, which is on actually applied computational fluid dynamics, so when we do CFD, you have heard many other lectures, when we go for CFD, then modeling of turbulent flows is a very important part of the, is a very important task. And now if we just recall these characteristics, so if we want to model turbulent flows, then it is a very challenging task, because the turbulent flow physics is very complex, as we have just seen. So why turbulent flow is computationally costly? So don't go by this number, but just don't go by the exact numbers, but see the impression. Suppose you take a flow on a plate of size 1.2 meter by 2.4 meter. And in this case, if you are talking about this size, first thing is we have seen that a turbulent flow is always three-dimensional. So even if you consider a flow on a plate of size 1.2 meter into 2.4 meter, it's a plate, but the flow on the plate will be actually three-dimensional. And if you take the smallest eddy size, 0.04 meter, sorry, 0.04 mm, then in this domain, you will have 5 trillion mesh points if you want to resolve turbulence. So this was, of course, very old in 1970. Now we have very fast computers 50 years later. At that time, they said that it will require 320,000 years with the computers that were available in 1970, 50 years ago, for this Reynolds number. nowadays, present days, if you want to do perform such kind of computation, I think in IIT Delhi we have one of the very good high performance computing facility. And if we want to do such kind of study now in India in some supercomputer, then still such kind of computation for this Reynolds number will take about 6 months to 1 year for a turbulent flow. So therefore, it's very important to understand turbulent flow and see if we can get the characteristics of turbulent flows without having to spend 1 year on supercomputer. And this is what we are going to trying to touch upon in this lecture. So we have just now seen the physics of turbulence, and we have seen the need for actually handling turbulent flows. So there are two key approaches. One is the direct numerical simulation and large AD simulation. So unsteady in this approach, in the first category, which you see on the top of your screen, unsteady three-dimensional Navier-Stokes equations for the instantaneous flow are solved numerically. And all scales in time and space are resolved, temporal and spatial scales. So this is DNS, and LES is, you can say, slightly less computationally expensive compared to DNS, but in the same category. In LES, the effect of small scales is modeled using subgrid scales. So what it means is that in LES also we solve unsteady three-dimensional equations, but we do not go up to the smaller scales. Rather, we model their effects. We write some equations to model the effect of the small scales. But both are actually quite computationally extensive, and we are working very. So both DNS and LES, we are not working on DNS because it is computationally very expensive, but we are working on LES. And both DNS and LES, because they are very computationally expensive, cannot be used as a design tool because of the large computational cost. The other approach, very widely used approach, entirely different approach, is Reynolds average Navier-Stokes equation, RANS equation. So in RANS equations, if you see very carefully, unsteady three-dimensional flow, we solve time average governing equations. But so I will show you later that when we write time average governing equations, we are all familiar with the Navier-Stokes equation, and then from that Navier-Stokes equation, I will talk about the time average equations. When we write time average equation, we will see that the number of unknowns increases. The number of unknown becomes more than the number of equations, and therefore we actually need some equations to reduce the number of unknowns. And in RANS, we actually model all the scales of motion. So numerical methods have an important role. And if you recall, in the previous slide, we have seen DNS and LES. I'm going to talk about everything. You see that actually in IIT Delhi, we offer a full course on turbulence and its modeling, which runs through 36 classes, 42 classes, 14 weeks, 3 classes per week, 14 into 3. And here actually it's very, very challenging task for me to present an overview of all these approaches in just 1 hour and 15 minutes or so. So in the Reynolds average Navier-Stokes equation approach, these are the types of models: algebraic model, 1 equation model, 2 equation model, Reynolds stress transport model. And we have seen it already in a large AD simulation. We solve 3D and Navier-Stokes equations unsteady, and we model the effect of the small scales. In direct numerical simulation, unsteady 3-dimensional Navier-Stokes equation solve for all scales in a turbulent flows. So if you just write one slide, first slide and the second slide, and go down, that means you go in the location of the pointer, then we model less and less number of scales, and we actually resolve more and more scales. As one progresses down the list, more and more of the turbulent scales are computed and fewer are approximated by models. Any questions so far?
Sir, we can take questions at the end of the session. to say.
Okay, okay.
Okay, yeah, because thank you.
So I can continue?
Yes, sir. Yes, sir. Please.
Okay, okay. So the session has to be finished by 4:30, or it can extend few minutes here and there?
Yes, sir. There is no issue.
Okay, okay. So just some more characteristics: wall bounded and free shear flow, turbulence in the presence of wall, and turbulence if there is no wall, then it is free shear flow. Homogeneous turbulence, if the turbulence has the same behavior in all parts of the flow field, that means at all points it is same. Isotropic is mainly because of the direction. If it is same in all directions. And we have seen very important characteristics that we have eddies of different length scales. And largest eddies. Now this is very important. So we have continuous change of size of the eddies from the largest to the smallest, and the smallest eddies are actually at the viscous level. So largest eddy size depends on the boundary conditions. For example, if you are sitting in a room, the largest size of the eddy will be as large as the dimensions of the room, and the smallest size will be at the molecular level. Suppose you go to the atmospheric boundary layer, then the largest eddy size will be several kilometers. That will be the size of the boundary layer, atmospheric boundary layer. So the largest size depends on the boundary conditions, and the smallest eddies that dissipate the kinetic energy into thermal energy, it depends on the viscosity. And we also see that very important characteristic here is there is an aircraft flying. So very important characteristic is that the size of the smallest eddies decreases with increasing Reynolds number. What does it mean? It means that if your Reynolds number is increasing, then the smallest eddy size is reducing. Or in other words, if your Reynolds number is increasing, then the range of scales is increasing, because largest eddy size, suppose you take flow through a pipe, you take Reynolds number at 10,000, then the largest eddy size will not change because it will depend on the dimensions of the pipe. But if you take Reynolds number 10,000 and 1 lakh, you increase the Reynolds number by factor of 10, then the smallest eddy size will reduce. And if the range of eddy sizes changes, then the problem becomes more complex, and turbulence is always dissipative in nature. Okay, so now I'm introducing the RANS equations, time average equations. So in turbulent flows, every flow variable is a function of space and time, x, y, z, t. So here it is u, here it is v, here it is w and p. We are mechanical engineers, and in mechanical engineering we mainly concentrate on incompressible flows. So we are not considering very fluctuations in density. And now when you say, so I have talked about time average flow. What is a time average flow? That means at a fixed point, I gave you an example of first slide, I gave you an example of the pressure velocity signal. So what do we do in that case? We actually, if you are at a fixed point in space, we go on taking the signal of u velocity, and we take the signal u velocity, average it. That means you take it over a period from t0 to t0 plus t, and you then divide it by the averaging period. You will get the time average velocity. So you see on the right hand side, it's just raw signal, and on the left hand side with the horizontal line u bar, actually it is the time average velocity. So this is called the time averaging. And in time averaging, most of the time, that on the left hand side, you see that the t is missing because it is steady flow in time average. Another method is ensemble averaging, in which you actually perform a large number of experiments. So you see that we are not averaging over time. We are actually performing large number of experiments, taking the signal and taking the average of that signal. So where n is a large number of identical experiments. So first is the time averaging, other one is called the ensembled averaging, and both concepts are known as the Reynolds averaging. So this is very important slide we are all familiar with the Navier-Stokes equation for the instantaneous flow. All of us have done in our bachelor's course, and most of us are actually, most of the participants here are master students or PhD students. So we have also done this in the PG level course. So what you see here is when we use this concept of time averaging and write every quantity as the sum of, so every instantaneous quantity is sum of time average and fluctuation. So if I see this slide, this was the raw signal and this horizontal line is time averaged, and the difference between the time average and the instantaneous quantity is the fluctuation. So we can see that the fluctuation is sometimes positive, it is above the horizontal line, and sometimes it is negative. Do this and substitute all these variables in the governing Navier-Stokes equation and perform the time average. We find that the time average equation, that the continuity equation for the time average flow is same as that for the instantaneous flow. So can you see my pointer? So can you see my pointer?
Yes, sir.
Yeah. However, if we talk about the U momentum equation, V momentum equation, and W momentum equation, then we find that each of these three equations has three additional terms which do not appear in the instantaneous flow. So here we have three additional terms which are fluctuating terms, and these terms were not present in the instantaneous flow. Just a minute. So please see this carefully. And the last equation is the equation for any variable phi. Phi can be so the phi can be temperature or concentration. So if we talk about isothermal flow, then we will not have this last equation, we will have only these three. So these three momentum equations. So what we see is how many additional terms we have in each momentum equation. We have three additional terms. So we have 9, but actually if you see carefully, these 9 terms are not there, but actually these are only 6 terms, because U prime W prime will be equal to W prime U prime. So we have actually 6 additional terms. So if we talk about time average flow, then and write the Reynolds average Navier-Stokes equation, that time average equation means Reynolds average Navier-Stokes equation, then we have 6 additional terms. So this leads to the closure problem, because instantaneous continuity and Navier-Stokes equation form a closed set of 4 equations with 4 unknowns if we talk about 3D unsteady flow. But the time average equations have these 4 unknowns, but there are 6 additional unknowns: rho U prime, rho V prime, rho W prime, and these one. These are called normal stresses and shear stresses. And we are presently not talking about the last thing, because we are talking about isothermal flow. So the number of unknowns is more than the number of equations, and it is a closure problem if we are talking about the time average flow. And likewise here you see in the previous case it was 3-dimensional flow. You can also write for 2D flow. In 2D flow we are very familiar with this equation. We have actually total 3 additional terms. There are 2 in this, 2 in this, but out of these 2, U prime V prime is common. So additionally we have 3 terms. So now we have to actually minimize these terms. So if we recall, for the laminar flow, the shear stress term is taken as mu t into rate of strain. So what we do is, like the laminar flow, we actually try to reduce the number of unknowns, and these unknown terms are called Reynolds stresses, Reynolds normal stresses, Reynolds shear stresses. So we want to minimize. So we use the Boussinesq approximation, and by the Boussinesq approximation, it's an approximation. The Reynolds stress term, so this 6 terms are written in the form of a tensor tau ij, is written as mean rate of deformation and the eddy viscosity. viscosity is different from the molecular viscosity, because eddy viscosity is actually a flow property. It is not a fluid property, as we have seen. And we can also write this for u prime v prime. That means if it is a thermal energy equation, then we can write this. So this is the Boussinesq approximation. So in order to reduce the number of unknowns, the number of unknowns was large. First thing is we use the Boussinesq approximation. But when we use the Boussinesq approximation, we get this eddy viscosity, which is a flow property. It is not a fluid property, so it will not depend on what fluid is being taken, but it will depend on what is the flow configuration that is being considered. So this is a closure problem. And now there are different models. Let me see how much time I have taken so that accordingly I can proceed. So already 45 minutes are over. So I have to give you an overview of everything. So I will only tell you the important things. So now the idea is, how do we calculate mu t? Okay, because once we know mu t, then we can find out the Reynolds stress, because mean strain rate is anyway being calculated. So there are a range of models. If you recall, I told you that 0 equation model, 1 equation model, 2 equation model. So actually, when we say 1 equation model, 2 equation model, please note very carefully that one word which is missing is the transport equation. When we say 1 equation model, it means we are using one more. What is a transport equation? Transport equation is like the momentum equation. A typical transport equation has, if you take the x component of the Navier-Stokes equation, unsteady term, convection term, diffusion term on the right hand side, viscous diffusion term, and the source term. So when we say 1 equation model, that means we are writing one additional transport equation. When we say 2 equation model, then we say that we are writing 2 additional transport equations. And when we say 0 equation model, it means that we are writing that we are calculating the eddy viscosity without writing any transport equation. But it does not mean we are not using any other equation. We might be using algebraic equation. Algebraic equation is not a transport equation. A plus B is equal to C is not a transport equation. So this should be very clear. And the last approach is the Reynolds stress transport model. Reynolds stress transport model is, we do not use the Boussinesq approximation. I will give you a glimpse of that. We do not use Boussinesq approximation. Rather, for each of these unknowns, six unknowns here, for example, we derive the transport equation. So what was the first model? First model that we saw was 0 equation model. 0 equation model is also called algebraic model because here we use an algebraic equation. So in the 0 equation model is also called the mixing length model. The nu t. So in the 0 equation model, the eddy viscosity is calculated by some algebraic relations. So we will not go into the details of 0 equation model because 0 equation model was being used 40-50 years ago. Mixing length model nowadays it is not being used, and therefore I think we should just skip this. So the next is 1 equation model. 1 equation model is also nowadays not being used. We will see why it is not being used. But in 1 equation model, we use one transport equation to calculate the value of eddy viscosity. And here, generally, in 1 equation model, it is the equation that is written for K. K is turbulence kinetic energy. So turbulence kinetic energy is fluctuations in turbulence. So U prime square, V prime square, W prime square. So we actually can derive a transport equation for K. And then based on this transport equation, we can calculate the value of eddy viscosity as shown here, L square root of K, where L is some length scale which is still unknown. So both 0 equation model and 1 equation model that we have seen briefly are incomplete models of turbulence, because these models actually need the specification of the geometry being considered. That means they will depend on the geometry that is being considered. If you apply one equation model for flow through a pipe, it will need some specification. If you go to some other geometry, it will need some other specification, and therefore it's a problematic situation. So we go to the next level of turbulence model, that is two equation model. So turbulence is characterized by some length scale and the velocity scale, and therefore we must use at least two transport equations to so as to have not the need for any specification. So any model which uses two equation model, which uses two equations or more, will be a complete model. And the simplest two equation model is actually a epsilon model. Most of us are familiar with this. So as the name implies, and as we have seen so far, K and epsilon. That means we are writing one equation for K, where K is the turbulence kinetic energy, and another one is for epsilon, where epsilon is the dissipation of turbulence kinetic energy, and dissipation is always loss of energy. So K epsilon model is very widely used, and it is the simplest complete model of turbulence. That means it does not need any specification. It's a two equation model. It is a high Reynolds number model. Again, in turbulence community, we don't use the word turbulence. It is for high turbulence Reynolds number. So for example, if you apply turbulent flow through a pipe, can you tell me what will be the level of turbulence at the wall of the pipe? At the wall of the pipe, no slip condition will be applied, and there will be no turbulence because of the no slip condition. So in other words, if you come from the center of the pipe to the wall, then center of the pipe to the wall, then the turbulence will die down and it will be zero at the wall. And in such case, this model cannot be applied. So it's a high turbulence Reynolds number model. In this model, the solution of two separate transport equation allows the turbulent viscosity and length scales to be independently determined. This is widely used for practical applications, and it is more expensive to implement than mixing length model because we use two transport equations, but it is not a universal model. It fails in many situations. So I will skip this transport equations of standard K epsilon model. Then we have this RNG K epsilon model. So as you can see, it's still the K epsilon model. So that means it still is the two equation model, but it is a different version of K epsilon model because it is RNG. RNG means renormalization group. It is based on renormalization. Model can be used close to the wall also. So we will skip these equations. So do you, Professor Bala, are you getting some disturbance because some construction work is going on in my neighborhood?
Yes, sir, but it is fine. It's okay.
Yeah, actually I told them many times to stop it, but I think they have to, evening they have to close. So is it okay? It's not too much, I hope.
Yes, sir, it is fine.
Okay. So we see that K-epsilon model has problems close to the wall because it needs some modifications close to the wall, and K omega model that we saw just now is not working well for the free stream. We have not seen close to the free stream. So the SST K omega model actually is a combination of K omega model in the near wall region, because K epsilon model fails in the near wall region, and it switches to K epsilon model when you are in the far field, close to the force of free stream. So shear stress transport SST K omega model in some sense that we see here takes best of both the models, K epsilon model and K omega model. And therefore it is very widely used even nowadays for many practical problems. So it is called SST K omega model. What is important to understand is that it's a combination of K epsilon and K omega model. So we will skip that. I think I will also skip algebra. So what is Reynolds stress transport model? Slightly different. So far in all the models that we have seen, we actually use the Boussinesq approximation. Boussinesq approximation means the Reynolds stress was taken equal to eddy viscosity and the mean strain rate, and all these previous models were used to calculate the eddy viscosity. But if we do not use the eddy viscosity, we do not use Boussinesq approximation, then we have to actually derive transport equations for these unknowns, 6 unknowns. These 6 unknowns. So in the Reynolds stress transport model, we do not use the Boussinesq approximation, rather we derive transport equations for these 6 Reynolds stresses. And that is actually a very difficult task. I will show you now how difficult it is. So if you write a transport equation for these equations in general form, you will get an equation like this. And you see that it has very, very complex terms. You see it is time average of 3 fluctuations. It is actually, you can see here, it is time average of pressure, instantaneous pressure and the strain rate. And you see here it is vorticity, and so there are many unknown terms, and if we want to write a transport equation, we do not know anything about these terms. Turbulent diffusion, buoyancy production, stress production, molecular diffusion, pressure strain, dissipation, and production by system rotation. And therefore it becomes difficult to model these terms. So the Reynolds stress transport model is the most complex turbulence model for the closure of Ray's equation. In the Reynolds stress transport model, we solve transport equation for the Reynolds stresses, and all these 6 Reynolds stresses will also have a dissipation. So suppose you have 6 Reynolds stresses, you will have 6 dissipation, but we write actually 1 equation for dissipation. That therefore we write actually 7 equations for 3-dimensional flow, and for 2D flow 5 equations, and therefore we write so many equations with so many terms, it becomes difficult. Therefore Reynolds stress transport models are not so widely used because of the problem in these modeling of these terms. So this actually brings us to the end of Reynolds stress models. I will just briefly touch upon turbulence in the presence of wall. So we are actually know this, that if you have turbulence in the presence of wall, then there are 3 layers: viscous sublayer, buffer layer, and fully turbulent layer. And most of these models, not all, but most of these models cannot be applied right in the vicinity of the wall. So how does wall affect a turbulent flow? One is the no slip condition, because of which there is no turbulence right at the wall. Then there is a viscous damping. Viscous effects become important close to the wall. And there is a kinematic blocking near the wall. And there are very large gradients in temperature and velocity field. So therefore, these models need to be adjusted close to the wall. And there are different approaches. I will not go into the details. One is the wall function approach. In wall function approach, we do not go right up to the wall. We take first grid point slightly away from the wall and we specify the velocities values. Other one is low Reynolds number approach. You can see the wall, but we actually need very fine mesh close to the wall. So there are different ways of handling turbulence in the presence of wall. And I think I will skip this and I will directly go to LES and DNS. So what is DNS? In DNS, as we have seen, when I gave you the example earlier of some flat plate and those dimensions, in DNS we have also seen earlier, we do not do any modeling. If we do not do any modeling, that means we resolve all the scales. And in other words, if we resolve all the scales, we also have to resolve the smaller scales. But the smaller scales are actually very small. And therefore, it requires actually very large computational resources. So DNS requires no modeling, but it demands resolution from large scales all the way through the beginning of the dissipation scales. So there are a range of scales. The smallest scales are called dissipation scales. These are very small. This is the most accurate approach to turbulent flow simulation. We solve the Navier-Stokes equation for instantaneous flow without averaging or approximation. And if we solve them numerically, there are discretization errors, numerical discretization errors, but using CFD techniques, you are doing a course on CFD, we can actually minimize these errors. And the cost of simulation in this case goes as RE to the power 3. This is very important. So suppose you take Reynolds number at 10,000, you have some computational requirement and you increase the Reynolds number by a factor of 10. From 10,000, you go to flow through a pipe, Reynolds number 10,000, then you go to Reynolds number 1 lakh. So factor of 10, but your computational requirement will go as 10 raised to power 3, 1,000 times. As we said that this cannot be used as a design tool. On large parallel computers, it is possible to do DNS. It is not easy, but it is possible to do DNS, but it can take large time. So since computational power goes as RE to the power 3, DNS is limited to small Reynolds numbers, and it contains so much of data that it actually becomes difficult to manage, and sometimes it is not very useful for engineering point of view. Then large eddy simulation, which is similar to DNS, but in DNS, in LES actually, we do not resolve the smallest scales. If we do not resolve the smallest scales, then our mesh requirement can be reduced. But smaller scales are important. So if you do not resolve them, then you have to write some equations to take care of the effects of the small scales. So LES requires modeling of the part of the inertial subrange and into the beginning of the dissipation scales, but we do not go right up to the smallest scales. And we use a cutoff length that beyond this, beyond some length, we are not going to reduce, we are not going to resolve, but we need some models. So LES resolve the large flow structures by selecting appropriate filter function. For example, if you see this range of scales, in DNS we go right up to this point, whereas in LES, smaller scales. So on the as you go in this direction, their scales become smaller and smaller because it is actually reverse of wave number. Wave number is actually inverse of the, here it is k is the wave number, which is inverse of the length scale. So if we go higher value of k, it is actually smaller and smaller scale. In LES, small scale actually modeled, and we write some filtered form of the Navier-Stokes equation. Why do we do this? Or can we do this? This is because one key characteristics which I mentioned in the beginning was that there are large range of scales, and the largest scales actually depend on the size of the boundary conditions. So in other words, if you take different flows, air in, for example, air conditioning duct, air, atmospheric boundary layer, air in turbine, all these have different length scales, large scales, because the boundary conditions are different. But in all these different configurations for the same fluid, you will find that the smallest scales or smaller scales are somewhat similar. So if in different flow configurations, smaller scales are similar for that. So the turbulent scales are characterized by eddies with a wide range of length and time scales. The largest eddies are typically comparable in size to the characteristic length of the mean flow. The smallest scales are responsible for the dissipation of turbulence kinetic energy. So in LES, large eddies are resolved directly while small eddies are modeled. And if you have small eddies which are similar, then it is easy to write models, and most of the dynamics of the flow is governed by the large scales. And if you compute large scales, then momentum, mass and energy and other passive scales are transported mostly by large eddies, so it works. So as we have seen, large eddies are more problem dependent. They are dictated by the geometries and boundary conditions of the flow involved. Small eddies are less dependent on the geometry and tend to be isotropic and more universal. So small eddies do not depend on geometry. They are somewhat isotropic and more universal, and therefore chance of finding a universal turbulence scale is much smaller for small eddies. And resolving only the large eddies and not the small eddies allows one to use coarser mesh. Coarser mesh means bigger mesh, the smallest mesh size can be bigger. So we can use coarser mesh and larger time steps than compared to DNS. So in other words, LES has most of the important characteristics of DNS, but it does it at the cost at a smaller computational cost. But it does not mean that LES is comparable to RANs that we have seen. It's still several orders of magnitude larger than RANs. So LES still requires substantially finer meshes than those for RANs calculation, and it also has to be done for a sufficiently long time. And the computational cost involved with LES is normally orders of magnitude higher than that for RANs calculations. So one order of magnitude, if we say 10 times typically. So several orders of magnitude higher means if RANs computation takes you 2 days, then LES may take 2 or 3 months, and DNS may take 1 year. So computational cost in LES is quite larger than that in RANs, but it is less than that for DNS. So nowadays we are working very extensively on large eddy simulation. In fact, my research group is working on large eddy simulation in climate modeling, cloud, combustion, and jet impingement, heat transfer, flow past bluff bodies, and many other situations. And these are the governing questions for this thing. So there is also, I think I will not go into the details. Nowadays, we are also very active in variable resolution models. So we have seen that, for example, if you see this scale, this we have seen earlier. This is the energy spectrum. And in RANs, actually, we model for all the scales. In DNS, we resolve all the scales. In LES, we resolve part of the scales. And then there is a variable resolution modeling approach in which we actually can go up parameters, and we can also go up to DNS. That means it adjusts between RANs and DNS. And there are 2 types of such approaches: hybrid modeling approach and grid bridging modeling. PANS approach is very important. Our research group is very active. If you visit my webpage, you will find that we have a lot of major contributions in the PANS approach worldwide. PANS is actually partially averaged Navier-Stokes approach. Partially averaged Navier-Stokes approach. And this is in some sense similar to LES, we get the features of LES, but at a less computational cost. So here there are some points about TANS versus LES. So I think I will stop here. I hope you are able to comprehend, you are able to understand and get some additional knowledge. And I'll be glad if to answer any question, if any, or to interact with you.
So participants can ask questions now.
So can you see me?
Yes, sir.
Any question? So I think Professor Baladath was mentioning that if there are any questions, he will compile and he will collect the questions and then maybe send it to me, and then I can think of responding.
Yes, sir, sure. Meanwhile, sir, I would like to ask you a question. Do we have any model which can be used across all such diversities?
Yeah, no. See, first thing is no. The answer is no. And it is not very difficult to understand why the answer is no, because turbulence is a flow phenomenon. And every flow is a different flow. So how can you have a model which works well for all flows? Because every flow is different. And we are years in trying to arrive at a model which works well. But no, the answer is no.
Okay. And sir, this is a common observation that whenever we deal with the software, no matter what, let us say if we are making any error in, but still software is going to give us some result, right? So how to take care of minimum error? For example, because turbulence, it can cause a very big damage to the result. So,
Yes. So see, the answer is not very simple. See, first thing is there are two different approaches. One is RANS approach, another is in LES. And RANS approach, there is no universal model which can work well in all the situations. But then if you apply it to a new situation, you can get help from the literature and find out in similar situations which model has worked well. In general, these days, many models have shown you K epsilon, no, SST K omega model is very widely used, which seems to be some sort of, I will not say universal, but of all the models, this seems to be a good one. And earlier people were using K epsilon model, K omega model, and there are several other models. Yeah, so it's not very simple. Coming back to your question, it is not very simple or easy to tell you in advance for a particular situation which model will work.
okay, sir.
Okay, so therefore turbulence research is very important component, or using a correct turbulence model is a very important component of your CFD computation.
Fine. So as we do not have any further questions from participants, so as sir we have discussed earlier, so if there is any query from participants, I'll compile it and I'll let you know through mail.
Okay.
And now I would like to thank Professor Anupam Dewan sir for sparing his valuable time. And sir, I think there is one question. Okay, it was in chat box, so I'll just read it out. How to get values of K and epsilon at boundary?
Which boundary? The value of K and epsilon will depend on the boundary. For example, the person who has asked me can simply answer this question. that K will be 0 at wall. Can someone tell me why K will be 0 at wall? Because of the no slip condition. Turbulence, K is turbulence kinetic energy, which is actually a measure of fluctuation. So K will be 0 at wall, but one can easily guess based on what I have presented that epsilon will be very large at the wall, because epsilon is dissipation, and dissipation occurs at the because of the viscosity, and close to the wall the effect of viscosity is very important because of the no slip condition. So K is 0 at the wall, dissipation is very large at the wall, or in other words, now if you go to free surface, a surface, suppose you take what you say, pond, suppose you take a pond and you see the free surface of a pond with waves, okay, because of the wind speed. So at the free surface, these values will be different, K and epsilon. If you are at the outlet of a pipe, these values will be different. So value of K and epsilon will depend on the location of the boundary.
Okay, sir. Fine. So with this, I would like to thank Dr. Anupam Dewan, sir, and thank you so much, sir, for sparing your valuable time and giving us insight on such a good topic, because the researcher who are working on this field are who are from thermal field, so anyhow they have to deal with turbulence.
Okay, I also thank all organizers for giving me this opportunity and to share my thoughts on turbulence and its modeling with all the participants. And I hope that it is useful, and at least when you are using the software and when you're talking about turbulence, at least compared to what you knew earlier, you will have actually more appreciation and a better understanding of at least the complexities involved with turbulent flows. And if you understand that it's a complex flow, it's still not well understood, the problem of turbulence. A lot of research is going on. We can understand why it is not well understood. And then at least while doing this, you will not use, suppose you are using some commercial software, you choose some turbulence model, K epsilon model, some condition. At least now after this lecture, with whatever little time you spent and heard, you will have a better appreciation, and you will be able to choose the turbulence model more carefully, at least. Thank you.
Yes. Sir, there is a small request. Could you send your PPT or something? Let us say if we want to convey the same to participants, if possible.
Yeah, this PPT cannot be shared. I'm sorry, because it's copyrighted material from my book.
It's okay, sir. No problem. Thank you so much, sir.
Yeah.
Have a nice day.
Okay, thank you. So I'm signing out now.
Okay, sir. Thank you.
Okay, thank you.
So I would like to thank all the participants for joining today, and that's it for day 3.